In lecture number 9, we used a method based on the principle of a minimum potential energy to derive a solution to one-dimensional truss problems similar to the types of one-dimensional truss problems that we solved previously using the direct method. And when we used the method that we derived in the last video, using the principle of minimum potential energy, we found a set of linear algebra equations which was the same as the set of linear algebra equations we found previously using the direct method. In this video, we're going to develop, using the principle of minimum potential energy, a method that will work on a more general class of one-dimensional truss problems. Up until now, our one-dimensional truss elements, we've always assumed that along the truss, that the cross-sectional area of the truss had some constant value A, and that the Young's modulus through the bar element had some constant value E. In this video, we're going to start developing a method for solving problems where the cross-sectional area length of our bar is not constant, but is perhaps some function of x. And also, we're now going to start assuming that our Young's modulus can also be some function of x. Furthermore, we're no longer going to assume that forces can only be applied at the endpoints or at the nodes of our bar element, but we're going to assume that there can also be some body force or some traction force or some function f of b, which is some function of x, which I use f of b here, but I shouldn't say that this is a force because this is like a linear pressure. So this function is going to have the units of either newtons over meters, or it might have units of pounds over inches. It works just like a pressure does, where you have to multiply the force, or you have to multiply the traction by some area, but in this case, it's some distance. Okay? So this is a more general class of problems. Now, before I start going into how we're going to do this, it'll be helpful to review some of the material that we've previously covered in previous lectures. You'll remember from lecture number 9 that we desire to come up with, find some function for the total potential energy stored in the system, and that this total potential energy is a combination of the internal strain energy inside the system, and then we subtract off the potential energy due to external forces, which is essentially lost energy because those forces are being used to create the strain energy. We're also going to start needing those shape functions that we had previously discussed way back in lecture 2, part 4. And why am I going to need those shape functions? So the goal of this method is to find the function u of x. And of course, I don't know u of x. That's actually what I'm trying to find. But the method is going to require us to approximate this function, assuming that we know the displacements at the nodes, at node 1 and node 2 in this case. Okay? So if you recall from lecture 2, part 4, and if you don't recall, I suggest you go back and rewatch that video, I can approximate u of x, assuming that I know the displacement at node 1 and the displacement at node 2. I can approximate that as 1 minus x over L u1 plus x over L u2. Or writing that in a more linear algebra way, I might say that u of x is equal to the rho vector 1 minus x over L times the column vector u1, u2. Remember, these are what's called the shape functions. And I might call this n1, and I might call this shape function n2. Now, what this means, of course, is that I can write this as shorthand. I can write u of x is equal to what is called the shape vector n, or it might be a shape matrix in some method we may develop later in this course, times the column vector u, where the column vector u holds my nodal displacements. Okay? And again, let's look at our at what this does for us. Remember that this shape function or shape vector n, this is the only thing that has x dependency. And this contains all of my nodal displacements. Okay? So this has this nice property that all of my x dependency is in one vector, and all of my knowledge of my nodal displacements is in another vector. This is the vector I'm eventually going to try to be solving for. Also, remember our notation that I'm using this to indicate a row vector. I'm using squiggly brackets to denote a column vector, and I will use square brackets to denote a matrix. Finally, let's remember that way back in Lecture 2, Part 2, we discussed taking derivatives of vectors and matrices. So for example, if I wanted to take the derivative of my shape vector, derivative of n with respect to x, that'll give me the vector negative 1 over L, 1 over L. And we will later learn that this vector is sometimes denoted by the letter capital B. All right? Now, in the next video, I will use some of what we just reviewed here to derive a formula or a function for the total potential energy stored in this more general bar element